The first thing we'll do in video 6 is to review the groups that you should know by name and be able to operate in them and know if they are abelian or non-abelian groups. The first groups that we looked at were just our regular groups, the integers, the rationals, the reals, and the complex numbers under regular addition, and Q star, R star, and C star under regular multiplication. And you remember that the star means non-zero. So these are just the non-zero elements of these sets up here, and they are groups under multiplication. Zn was a group containing the elements 0, 1, 2, 3, up to n minus 1, and it is a group under addition mod n. Un is the set of elements in Zn that are relatively prime to n, the set of A in Zn such that, or where, the GCD of A and n is equal to 1. This is an abelian group under multiplication mod n. And then the 2 by 2 matrices with real entries is a group under matrix addition. For non-abelian groups, we have looked at the general linear group, GL2R, that is the 2 by 2 matrices with real entries with determinant not 0. Those form a group under matrix multiplication. And of course, it is not an abelian group. Now, the special linear group, that's a subset of GL2R, and it is the set of all 2 by 2 matrices where the determinant is equal to 1. And it's easy to argue for closure there too. So you should know these, memorize what they are, memorize their definitions, and then be able to prove, if asked, why each one is a group. You prove closure, you mention associativity, you find the identity of the group and prove that it is, and then you pick an arbitrary element of the group and show that it has an inverse in the group. Last time in class we looked at D4, the symmetries of a square. So I think this will be really easy for you to think about. The symmetries of an equilateral triangle, D3. You see here there are 3 lines of symmetry, lines of reflection, and the rotations would be 120 degrees. Right, R is a 120 degree rotation. And so R squared is R followed by R, and that would be 240 degrees. And then R cubed would be followed by another 120, would be 360 degrees. R cubed just puts the triangle back to where it was. So we have 3 rotations, and we have 3 lines of symmetry. Notice over here, if we were to reflect around the line S0, that we would put the triangle, it would be a 1-to-1 mapping of the triangle onto itself. If we call one of those reflections, and it doesn't matter which one, let's just call one of them H, then the other reflections are, if H happens to be the reflection around S0, then HR and HR squared are the other 2 reflections, one about the line S1 and one about the line S2. And you can see that there are only 3 lines of symmetry and 3 rotations that would map the triangle back onto itself. So that's how we get the 6 elements of D3. the calculation rules in D3 is the following. We know that r cubed is equal to the identity. We know that h squared is equal to the identity. Just think about it. If you flip over the line S0 and then you flip again over the line S0, you've just landed the triangle back where it was. So that means that h followed by h is e. Also, I'm going to write it down here because it's not really in the set of calculation rules, but hr squared is a flip and hr squared is another flip. So if those also, if you do them twice, give you the identity. But as far as a set of calculation rules, r cubed equals e, h squared equals e is almost sufficient. You also need to know that hr is equal to r squared h. And hr squared is equal to rh. And given these 4 calculation rules, you can do any calculations in D3. Notice the little table I made here. Just like you made for your homework, I did it for D3, and I colored the identity red, and every box that had an R in it I colored purple. And look at the design that you get. And you see a pretty symmetry occurring here. This is D4, the symmetries, or one-to-one mappings of the square onto itself. The symmetries of a square, D4. Now, notice I used a little bit different notation here, and I want you to take note of this. This means that the group is generated by just R and H. Generated by R and H. That means that if you take all powers of R, all powers of H, and all products of those powers that you take, that you will have the entire group. And it's easy to see. Look, if we take first the powers of R, we get those. We get to R to the 4th, and we're back to E. Then we have H in there, R and H. If we take the power of H, H squared is E, and then we multiply HR squared, and HR cubed, and we have the entire group. So jot this down. This means that D4 is generated by R and H. And in fact, that's true of all dihedral groups. Let's go over the calculation rules here. We know that R to the 4th is equal to E. That's very important. And we know that H squared is a reflection across a line, so if you do it twice, you're back to the identity. And then we need to know how to calculate powers like this. HR is equal to R cubed H. HR squared is equal to R squared H. And HR cubed is equal to RH. Notice that if you add the exponents, you get 4. For example, this is HR to the 1. 1 plus 3 is 4. HR squared, turn it around, subtract 2 from 4. HR cubed, if you want the H on the other side, you subtract the exponent from 4 and you have 1. Each time those exponents add up to 4. So these are the calculation rules for D4. And using them, you can calculate just about, well, anything that you're given in that group. For example, let's calculate HR squared times R cubed H. And why don't we take the inverse of all that? Make it complicated. Okay, there's different ways you can do this. You could, because you know it's a group, you could just write down equals and then write H inverse, R cubed inverse, R squared inverse, and H inverse. Just reverse the order, but I'd rather not do that. I want to calculate what's in here first. So I would like to, well, first of all, R squared times R cubed, that is H R to the fifth. And R to the fifth is R. So then we have HRH inverse. We had R squared times R cubed is equal to R to the fifth, which is R to the fourth times R. But R to the fourth is the identity. Actually, with the powers of R, you're just letting the exponent be the remainder upon division by 4, or mod 4. Okay, well, I'm still going to just work on the inside here. I'd like to change RH into, let's see, we have H. RH is HR cubed. And I wanted to get the H's on the left, and I see that I have 2 of them here. So they cancel. HH is the identity, and we have R cubed inverse. Now the inverse of R cubed is the element that when you multiply it to R cubed, you get the identity. Well, R cubed times R is equal to E. So this R cubed inverse is R, and that's the answer. In general, D sub n is a group generated by R and H. R being a rotation, R is a rotation, and let's just say counterclockwise, a rotation of 2 pi divided by n radians. And so R squared is a rotation of 4 pi n. 4 pi over n, I mean. Let's say R to the k is a rotation. Well, it's R followed by R followed by R k times. But if you think of it as all one rotation, you can think of it as the rotation of 2k pi divided by n radians. And of course at the end you have 2n pi over n, which is 2 pi, getting you back to the original regular n gone. And in this group, it is always true that R to the n is equal to E, H squared is equal to E, and here this is stated in general. We haven't done that before. R to the k, H. If you want to put the H on the left, it's HR to the n minus k. Notice the sum of the exponents on R add up to n. So this little formula is true for k equals 0, 1, 2, up to n minus 1. And these are exactly the rules we had in D3 and D4. And look what I happened to find when I was looking online for an example for you, and I found the Ashoka Chakra, is that how you say it? Is an example of two-dimensional symmetry, D24. So you could think of these little things here as being where the vertices of a 24-gon are, and these spokes here could be the 24 lines of symmetry. So we get to this on the next slide, but this is called the order of D24. It is not absolute value. It means the number of elements in the group. And that's written on the next slide. But the order of D24, you have 24 rotations and 24 reflections. So the order of the group is 48, meaning we have 48 elements in the group. Now this means something different. When you put the absolute value signs around an element of the group, it means the order of the element. And that is the smallest positive exponent on HR to the fifth that will give you the identity. So the order of, we know that's a reflection. If it has one H in it, it's a reflection. So we know that its order is 2 because HR to the fifth squared is equal to the identity. We'll get to that on the next slide. The order of R is, well, the order of R is n, and that is 24 in this case. So this next example is to do a calculation in D24. Well, I underlined the R to the 7th times H because I want to get that H on the left-hand side. And that is easily done. I'll write down my H. And now I want to write R to the 7th times H as HR to the 24 minus 7, so it would be R to the 17th. And then we have our other R here, and we're going to cube that when we're done simplifying the inside. Now the HH is the identity in any dihedral group, so this is equal to R to the 18th cubed, so it will be 18 times 3. But remember, this is mod 24, so I'm going to write that here. You don't have to, but we're going to multiply 3 times 18, but our exponent will be mod 24. So 3 times 18 is 54, and mod 24, well, I'd subtract 48 from that, so I get R to the 6th. And my answer is R to the 6th. We always want the answer to be written like one of the elements in the group. H is on the left if there is one, or a power of R, where the power is less than 24. Okay, the next calculation, RH, R inverse. Well, I think I would still go with the strategy of getting the H on the left. So I'm thinking of just RH here, and we are in D24. So RH is HR to the 23. And I want to multiply that by R inverse. So we'll just go ahead and add these exponents and get R to the 22. And this is one of the group elements, HR to the 22. Well, these are the definitions that I probably should have put before the last slide. These should be memorized. All definitions need to be memorized word for word. The order of a finite group, G, is the number of elements in that group, and it is denoted by this. And it looks like absolute value, but of course it is not. It just means the number of elements in the group. It gets a little confusing because the order of an element A is also denoted by this, the order of A. And so you have to read those bars as the order of, but if there's a group inside those bars, it means the number of elements in the group. For example, the order of Z6 is equal to 6. The order of the dihedral group Dn is equal to 2 times n. The order of an element is the least positive integer n, such that a to the n power is equal to e, and it's denoted by the order of A. Let's look at some examples of that. you verify these examples if they're not obvious. In the group D6, the order of R is equal to 6. In the group Z6, the order of 2 is equal to 3. Why? Well, think about it. 2 plus 2 is 4, plus 2 more is 0. So we have 2 plus 2, 2 plus 2 plus 2. The order of 2 is 3. In the group U5, remember that would be 1, 2, 3, and 4. The numbers from Z5 that are relatively prime to 5. In this group, the order of 2 is equal to 4. Why? Because 2, we have 2. 2 times 2 is 4. Times 2 is 3. Times 2 is 1. So we have 2, 2 squared, 2 cubed, 2 to the 4th is equal to 1. And so is 2 to the 8th, or 2 to the 20th. But 4 is the least positive integer, such that 2 to that power is equal to the identity. So we say the order of 2 is 4. And we're going to end this video with a very important definition. Let G be a group and H be a non-empty subset of G. H is a subgroup of G if H itself is a group. Under the operation of G, we use this notation. You can always just use the less than or equal to sign. Sorry about that. You could always use the less than or equal to sign, but if you know clearly that it is a proper subset, you could use this notation too. It means H is a subgroup of G. So let's look at some examples. Let's say that we are thinking of the group being D4, and the H, the subgroup, is the set of rotations, E, R, R squared, and R cubed. We can say that H is a subgroup of D4. Why? Well, think about it. H is closed. H is closed under the operation in D4 is function composition. We know that. We know that the operation is associative. That's inherited from the group D4, so that doesn't really even have to be mentioned. It is true that E is an element of H, so we have the identity. And the inverses are all there. Inverses are there because the inverse of a power of R is just another power of R. Now, here's another example. You could say, well, U6 is a non-empty subset of Z6. True, but it's not a subgroup. It's not a subgroup because U6 is not a group under addition. The operation in Z6 is addition mod 6, and U6 is not a group under addition mod 6. It's a group under multiplication mod 6. Think about it. U6 is equal to just a two-element set containing 1 and, see, not 2, not 3, not 4, 1 and 5. That is U6. Notice if we add 1 plus 5, we get 0, and 0 is not even in U6. So we have an example of a subset, but it is not a subgroup. The first way that we will learn to test a subset to see if it is a subgroup is the two-step test. It's very easy. You just check to make sure that the non-empty subset is closed under the operation of G, and you check to make sure inverses exist for all H in H. If they do, then you have a subgroup. Now, let's just see why this is true. Number one, you know that the operation is a binary operation, and you know that G is closed under the operation. So you should definitely show that H is closed. The other part of being a binary operation does not need proving, because we already know that if you operate in G, you get one unique result. We could say associativity is inherited from G. There's no need to prove that. So you don't even need to mention it. You do need to verify that H is closed under the operation. Now, 3, yes, we do need an identity, but if we prove that inverses exist, A inverse is in H for all A in H. Well, if all the inverses are in there, then, and you know it's closed, you've already proven it's closed, then A inverse is equal to E has to be in H, so you don't need to prove that. All we need to do is prove closure, and that for every A in H, A inverse is